Okay, welcome to the April Mount Diablo Astronomical Society General Meeting. Can everybody hear me okay? Okay. Just some quick announcements because we got an action-packed meeting this evening. I sent out an email. If you did not see it, we're having a memorial remembrance for David on Thursday, May 8th at 11 a.m., the Mount Diablo Lower Summit parking lot. If you want to join, please look at that email or email me because Beth Rainsford is organizing that and she would like a head count. And there'll be lunch at Rocco's in Walnut Creek afterwards. Are there any new members in the room tonight? Okay, welcome, welcome. Thank you for coming. If you need to use the bathroom, they're going to go right through these doors here. We're going to have a break after our What's Up presentation before our main speaker, so you can go then as well, and we'll have snacks in the back during our break. Our next public astronomy night is this weekend, Saturday, April 26th. If you haven't RSVP'd, Marnie, do they still have time? Oh, no RSVP, sorry, this is the public night. So just go ahead, head up on the mountain. It's a lot of fun if you've never been, and the big telescopes are out. Okay, we're gonna jump real quick. A reminder, if you're doing any public outreach or want to pass out cards at any events, we have our public astronomy nights and our Mount Diablo Astronomical Society cards up front. So grab a stack full of those before you go. Okay, we're gonna get quickly on to Renee Gandolfi. He's going to give us a quick announcement on our Yosemite Star Party, and then he is our What's Up speaker for the evening, giving a Haley's autobiography. Go ahead, Renee.
Hi, folks. Yosemite, as far as we know to this moment, is happening for a star party. Every kind of week since the election, I've wondered whether or not the National Park Service will exist at that point. But I'm told that we are on. Our weekend is July 31st to August 3rd. This year, they are going to allow us to go up there on Thursday to start the camp. So if you're signed up, you will have, I'll get one of these to you when I've got everybody signed up. It's a pass. When you get to the front gate, if there's somebody there, you'll show them the pass so that you can get into the campground. At this point, we're using Bridal Veil Campground. The facilities should be a lot better than they were before the fires. The new National Park Service coordinator is a little bit bureaucratic, so she requires lots of contact from me and lots of paperwork. So I'm probably going to have to make sure that if you're going, you're signed up on the list for the Park Service as one of the volunteers. Turns out it's a waxing crescent moon. It's going to set around midnight Friday and a little later on Saturday. So the west horizon is going to be kind of white. And that's the announcement for now.
We have a quick question.
Yeah, just a quick question. So I heard July 31st is the start. What was the end date for the start party?
July, what?
July 31st is when it starts.
It's from Thursday, July 31st to Sunday the 3rd. So the campsite, you'll have campground access at the volunteer campsite on Thursday night, Friday night, and Saturday night.
Excellent. Thank you.
Okay. Go to the front desk.
This way or that way?
Okay. Whatever you put on. All right, let's go to from the beginning. Should let you start.
Yeah, I was just looking for the slideshow.
Okay.
Slideshow.
I always wonder how we got to the moon on our first try after we do stuff like this, and it takes us forever. I handed out a piece of paper with Edmund Halley facts. I will point out that there are two things on there that are not true. So it's your job tonight to figure out which one they are. We'll see if you were listening. Let's see. So Edmund Halley was a great Grateful Dead fan. and while he was at Oxford, always wore this shirt. Not true.
I'm sorry, what was the other one not true?
He was born in 1856 in October. In 1656. In 1673, at the age of 17, he attended Queen's College, Oxford. So he's like 17 years old. 3 years later, he ends up on a ship, the Unity, sailing to St. Helena in the South Atlantic. And his job there, self-imposed job, is to survey the southern sky. One thing that we're going to get tonight with our presentation later on, astronomy has kind of changed in the last centuries. In the time of Halley and before, it's astrometrics. What they're trying to do is measure where stars are, identify stars. And so the entire southern hemisphere is terra incognito, and he goes to do that. He ends up on St. Helena, and he sets up an observatory. And with this is the remnants of it on the island, comes back with a star chart of some 300 stars that nobody knew about in the northern hemisphere. He takes with him about a 5-foot-long mural sextant, and the way these things were set up is you'd set it up on the meridian, and you'd wait for the star to come by, and then you'd measure it, and you'd have to know what the time is, and you'd have to know a whole lot of other stuff, and recognize this is a time before we really knew how to measure longitude, because it wasn't until we got very, very accurate clocks that we could do that. Halley wanted to say, could we figure out longitude by phase of the moon, angles of the moon, some other celestial things? So he spent lots of time looking and cataloging. In May of 1677, he observes a lunar eclipse. Later on that year, actually 2 weeks later, he observes a solar eclipse. And he starts, again, charting where the moon is, charting where the sun is. There's a transit of Mercury on October 28, 1677, and after observing that one, he predicts that you can take transits and use the measurements to accurately measure the distance between the sun and the earth, which we didn't know at the time. And what he's doing is he's saying, if you've got distant observers on a sphere, you can measure parallax, you can measure things like that, you can then do the algebra and the geometry to figure out the distances. A little while after that, he goes and consults with a guy named Cassini. And Cassini says to him, hey, you know those things in the sky that we see things like this? Well, they're not atmospheric phenomena. They're further away. And so Halley is starting to think about comets already at that age. Next thing he does is during his sailing, he notes that the length of the pendulum in his clock was different in England than it was in the South Atlantic, and he uses that information and gives it to Newton. And Newton ends up showing that gravity must be lower in the southern hemisphere, or at least where his observing was, based on what calculations that Newton was doing. In May 1679, he goes up to Danzig and visits Helvetius and observes with him. And Helvetius was one of the very famous astrometric astronomers at the time. Those of us who go up to Yosemite or up to the top of the mountain and haul our stuff and bitch and moan about how hard it is to move it around, this is what you have to deal with. This is also what Helvetius and his wife used. So everything is optical, everything is analog at this point. And what Halley does is, while observing with Helvetius, they're comparing notes for, I found this star at this point, I got it at this point, and it's this many degrees, et cetera, et cetera. So they're constantly refining what information they've got. And then in 1682, he sees something that came around in 1066. And if you're familiar with this tapestry, there's a comet in 1066 heralding the Magna Carta, but it also, after Halley comes and calculates stuff, it's the same comet that came back a number of years later and a number of years later, and he says this one's coming back in some 70 years, and this is when. And in fact, he was right. He didn't live long enough to see it happen, but his stuff was out there. He's elected to the Royal Society as secretary, which is like a new position. He edits the philosophical translations and gets them published. Then he goes off to India and tries to calculate longitude in India. He eventually develops a device that is the modern sextant. In 1683, he's working on the motions of the satellites of Saturn. In 1683, he works on magnetic variation in the South Seas, and he's the first one to write an essay on the theory of the origin of the magnetic field. In 1684, he goes off and studies tides. Some of that because of his interest in the moon, some of it simply because he's into surveying, looking at things and stuff like that. 1686, he ends up publishing a treatise on trade winds. The symbols and charts that he used on his charts are still used in weather charts nowadays. He proposed that solar heating causes atmospheric motions. He established the relationship between barometric pressure and height above sea level. Then in 1686, the Royal Society says, hey, we want you to go to that guy Newton and get his stuff published. Let's get it out there. And so in June of 86, he says, I was ordered that Mr. Newton's book be printed and that Mr. Halley undertake the business of looking after it and printing it at his own charge, which he is engaged to do. So those of you that want to be grateful to Isaac Newton, we got to be grateful to this guy because it wouldn't have gotten published without him. In 1687, Principia is published. He doesn't get a whole lot of credit on the cover for it. And then in the same year, he publishes a paper on cubic and quadratic equations. And here is a portrait, and he chose to have his notes involved in that portrait when he was at Cambridge. 2 years later, he surveys the mouth of the Thames and the coast of the North Country. So he's pretty much busy on sea. He's busy with the Navy. As part of a salvage operation of a ship off the Thames, he develops diving equipment to be able to bring this galley up. He's one of the first people that probably suffered barotrauma to his ear. In 1691, he goes and determines where Julius Caesar landed from the Downs in England by analyzing historical records, fixing the year by an eclipse and the date based on lunar phases as listed in Caesar's commentary. He infers the location considering the Caesar mentioned high ground, Dover. Knowing the course of the tides in the Straits of Dover and are affected by the phases of the moon and general sets of winds and straits, he pinpoints the location. Caesar landed on the 26th August, 55 BC in the lowland between North and South Forelands near the present town of Deal. So now he's doing archaeology by doing astronomy. In 1692, to explain the magnetic field of the Earth, he proposes a model where there's a hollow sphere with a shell 500 miles thick and 2 inner shells plus a core. He was wrong. Can't always be right. He put forth the idea of the hollow Earth consisting of shells, and he proposed that each shell had a magnetic field and a magnetic pole that were each revolving at a different speed. He proposed a scheme to explain the anomalous compass readings that he was getting. He speculated that escaping gases caused the aurora borealis. So again, not quite. But he did suggest auroral rays are due to particles which are affected by the magnetic field, the rays parallel to the Earth's magnetic field. In 1687 and 94, he devised a method for obtaining numerical solutions to polynomial equations by successive approximation. Sounds a little bit like what Newton's doing too. Two papers referred to the origin of cubic and quadratic equations and the problem of the intersection of the parabola with a circle. And he holds one of the diagrams in his portrait. All this is so critical to his being able to calculate where comets are going to be, where planets are going to be. All this essentially spherical geometry. In 1693, he studies life annuities in Breslau and is one of the first people to come up with an actuarial table for life expectancies. He has short papers in 93 to calculate the focal length of a thick lens and the transmission of light through transparent materials. And then he establishes that the greatest size of the gold atom could be used by physical experimentation with gilt wire. He's off by 3 orders of magnitude, but small stuff. He's looking for a way to establish the size of the solar system, distance to the sun, and so he proposes locations for simultaneous observations of the transit of Venus in 1679. And that becomes the impetus for a guy named Cook to be sent sailing to the South Seas to Tahiti to do the observations. He then works with the literature from an Arabic astronomer from 800s to determine celestial positions of the sun and the moon during the seasons, as well as report on specific solar and lunar eclipses. With this information and with the observations of the orbits of Jupiter, he figures out that the orbits of those moons is being affected by the tidal bulge of Jupiter. And he concludes that the moon's orbital speed would be, Earth's orbital speed would be increasing with time. In 98, he takes command of Paramore, a Pink, and he sets sail for his second sail into the South Atlantic, as in the uniform of a commander in the Royal Navy. Is one of the, there are only like 5 portraits of him. So he ends up sailing all the way from 52 degrees south to 52 degrees north and charts magnetism, charts trade winds, and charts longitude of places and stars. He comes up with magnetic field lines that he's able to publish, and again, these isobars of magnetic strength are a way to chart things on weather charts and stuff like that that he created. They're called Hallian lines. He ends up sailing in the third sailing in the English Channel, charting the English Channel for the Royal Navy and the Queen. Queen Anne then sends him to the Adriatic to be an envoy. He comes back and he's elected the 4th Sylvian professor at Oxford. And here he is when he's not going to a Dead concert. In 1705, he publishes Astronomiae Cosmetica, which is his method for calculating comet motion, tables of comets, and diagrams. Then he goes and he translates something out of the Arabic and corrects things that are found in the previous translation because he says they didn't know how to speak Arabic, plus they didn't know math. He edits some of Flamsteed's stellar catalog and sees that it's published along with the volumes of the Historia Colliatus. So he's hot to get more stuff into the literature so people can compare it. Then in 1715, he calculates the path of a solar eclipse in England. And he does this because he wants to let people know there's nothing mysterious about this. And also because he wants to get other people who are good observers to chart this so he can do measurements of the moon, so he can do other measurements. He observes the solar eclipse and he identifies Baily's beads. and correctly predicts that they're caused by variations in lunar silhouette. He publishes, previous one was his publication on the use of parallax to measure transits, to measure astronomical distances. He discusses the proper motion of fixed stars, and he compares his observations with that of Ptolemy's Almagest. And he determines the proper motion of Arcturus was 30 arc seconds in 1800 years, and the proper motion of Sirius was 2 arc seconds since Tycho's observations. So he's getting down to arc seconds with this type of equipment. I can't do arc miles. In 1720, he succeeds John Flamsteed as royal astronomer, and this is the mural quadrant that was established at the observatory. And then a number of years later, 1642, he dies. Okay, you are all listening carefully.
Okay, so I take it he didn't go to Grateful Dead concerts.
He didn't go to Grateful Dead concerts. That's one. What's the other one?
Unless they were some sort of Baroque band or something. But
Anybody? Not right. What was that?
When did you say he died?
Louder.
When did you say he died?
1742. The one that is wrong is, I just want to see exactly how it got written on there. Yes, it's the first line, Sir Edmund Halley. He was never knighted.
Oh, wait, he was never knighted?
He's never knighted.
Then why is
Blasphemy.
Newton was, Halley wasn't. And for those of you that want to delve into it a little more deeply and also want to get into some of the mathematics, this is the book that I took all the information out of, and incredible diagrams and explanations that I can't even do. So I'm just amazed at this guy. It's like sort of like Halley, comet, okay, that's all of it? No. Thanks.
What's the name of the book, Renee?
Name of the book is Edmund Halley, Charting the Heavens and the Stars. The author is Cook. Yes.
A bit of trivia about his comet, Halley's comet. It appeared in the year, I believe it was about 1824, the year that Mark Twain was born, and it appeared again
In the early
the year
1900s.
that Mark Twain died in 1910.
Right. Yeah, and he didn't survive into the first reappearance, the one that he predicted. It happened, I think, in the 1760 or something like that. So although he was right, he didn't get to do it. But still, it's just amazing to work with stuff like that. So thank you, folks.
Any other questions?
Yes.
One
Yes.
more right here.
Did he meet John Harrison?
Did he meet who?
John Harrison?
I don't know.
Oh, he's the one who figured out the longitude.
Yeah, no, but wasn't that mid-late 1700s when the clock was done?
It was about a century later when Harrison's chronometer was made.
When they first got the chronometers that
100
worked.
years.
the late,
What's, you know, you were there.
1700s, about
Yeah, so
1760 or so. Cook carried, I think, one of the first ones
yeah.
on his voyage.
Yeah, and the Royal Navy, I think, or the Admiralty had a 10,000-pound prize or something like that for whoever could first come up with it.
Get it.
Yeah.
John Harrison got it.
John Erickson was one who got it. Yeah.
Harrison never so much as it.
No, he did get it.
The family eventually.
Yeah, it took a while.
Yeah.
How did he calculate longitude then? I know there's a moon method of the eclipsing of
He's-
stars, that kind of thing. Was
He's
that around then?
He's calculating it by what the two sides of the moon are visible. In other words, what the angle is of the lit portion of the moon, because that's going to change with time. He's doing that also from distance from the horizon to where the moon is. So from tables of lunar motion, he should be able to say what the absolute time is. But you've got to have incredibly accurate devices to do this. And something that I didn't realize is every time you get near the horizon, you've got all the atmospheric stuff that's changing your angles. And then you've got to calculate those in. And it's beyond what I can imagine.
He was able to calculate the bending
yeah,
of
and
the
they
light
were.
at
He
that
wasn't.
time.
He wasn't great. I mean, it was. If you were sailing a ship and you're off by a degree, that's you've lost your fleet. If you're calculating it from stuff and you're off by 1 degree out of possible 90, you're doing pretty good. So I mean, at this point, he's getting close to where some of these places were, just by calculations without having a chronometer.
All right, everybody, let's give Renee a huge round of applause. Thank you. So now, just a reminder real quick, Renee did this out of an interest of his own, and he gave a What's Up talk because of his, passion about astronomy and learning. And we're always looking for people to give presentations. It wasn't too scary, was it? These people weren't too mean to you, were they, Renee? So if you have an interest, if you want to do a What's Up, you can email me, talk to Kent. I'm sure a lot of you have a lot of interesting interests that you could research and share with us. Okay, we're going to take a 10-minute break. Oh, Kent.
I was just saying, we want to hear your stories.
We would love to hear your stories. Okay, 10-minute break before we get to the main presenter. Thanks, you guys. Okay, we're going to continue with the program. I'd like to introduce our main speaker for the evening. Welcome, Professor Stephen Kahn. Dr. Kahn is the Dean of Mathematical and Physical Sciences and a Professor of Physics and Astronomy at the University of California, Berkeley. He has also held senior faculty positions at both Stanford and Columbia Universities. Prior to assuming his current position in 2022, Dr. Kahn was the director of the Vera C. Rubin Observatory construction project. He is a distinguished experimental astrophysicist who has made major contributions to X-ray astronomy as well as observational cosmology. Dr. Kahn is a fellow of the American Physical Society, the American Association of the Advancement of Science, and the American Academy of Arts and Sciences. If you could please welcome Dr. Kahn. His presentation tonight is the Vera C. Rubin Observatory.
So thank you very much for inviting me. It's always fun to give these presentations. That was a fascinating talk about Edmund Halley, in the history, obviously a key figure in the history of astronomy. So what I'm going to tell you about today is also a bit of history. As Tara mentioned, I was the Rubin project director for 9 years. I started working on this project in 2003. The idea for it goes back to the mid-90s. And I'll tell you some of the history and give you some of the details. But the historical news is after, I don't know, 25 years, we took first light exactly 1 week ago today. That's a little bit of a secret because we're going to hold a press conference in June and they'll announce the first light and show some of the first images. I can't show you the images because they're embargoed, but I will give you a lot of the background about what's happening. So Rubin is a major project, a major federal project. It's a $1 billion class project. So these kinds of projects take a long time from conception to getting them approved, getting funded, and then of course getting them built. And we had a large team of people involved in this. We had a mission statement. You know, our mission is to build a well-understood system, and I'll come back to that, that will produce an unprecedented amount of astronomical data for studies of the deep and dynamic universe and make the data accessible to a diverse community of scientists and engage the public. So well understood is crucial. As you'll see, what Rubin really is a statistics machine. Every category of astronomical object that we know about, Rubin will detect and catalog 10 to 100 times as many of those same objects. So we take lots of sort of known phenomenology in astronomy and cosmology, and we bring the statistical level up that we can do rather precise measurements. Now, when you do that, of course, you have to worry about systematics. So that was a key element of our design right from the beginning, was to build a well-understood system. And it isn't really the convention in astronomy, even professional astronomy. The previous history was sort of build a system, get it working, and we'll figure out how it works once we're on the sky. We couldn't afford to do that here because there were going to be assumptions that, you know, that were going to go into the final analysis. So there was a lot of emphasis. One of the reasons it took a long time to happen, a lot of emphasis in understanding every element of the system quantitatively at the unit level, and then calibrating that up, putting it all together, recalibrating, so that we have a very precise piece of instrumentation at the end. So this project started from a science-driven idea, and I'll go through the science. It's a big project. We need a lot of people to work on it. We needed funding. We needed a location. Let me say something about a lot of people to work on it. The way most big telescopes are built, the money is awarded to some institution, and that institution goes and hires the people to build it. This project was so challenging, we couldn't afford to do that. So we went to recruit the best people in the world in all the individual technical elements. We weren't going to move them all to one place in the country. So we just said, stay where you are, and we will work as a distributed team. That was quite unusual at the time we started this. Pre-Zoom, okay? It was not easy to do, to manage a project that was widely distributed that way. We had to learn how to do that. And also, you know, there are regional rivalries. One group at one institution starts arguing with another group. That's the usual thing you have to get to. But by building the project from the ground up that way in terms of people, we had tremendous loyalty. I've never seen a project like this before. Most of the people working on it were with the project for 20 years. And very few of the original people involved have left. One of the people that left was me. And I should just comment on that. We were supposed to have first light in 2022, in May of 2022. COVID hit in 2020. We lost 3 years. We had fabricated most of the components. They were being built all over the world. They were in the process of being shipped to Chile. As COVID made its way around the world, it hit us basically in every location. So we effectively lost 3 years. At that point, I decided to take my current position as dean. It's now exactly 3 years later. We did get first light, and that's basically the COVID thing. But most of the original staff are still with this project. So we needed a great site. We chose a blank mountaintop in Chile. We created a data center. This is one of the largest data projects in astronomy. It's the largest that's ever been built in astronomy. And we had to build nearly everything from scratch. Every element of this system was pushing the state of the art. And I'll go through some of that as we go on. So this project has a long history, and it's gone through some name changes. So you may have heard of it under different names. It was originally called LSST, which at the time stood for Large Synoptic Survey Telescope. That's one of those terrible names that gets generated by committee at some early time, but it was familiar to people, so we used it. As I'll mention later, we renamed the project about 5 years ago after Vera Rubin, who was one of the pioneers of observational astronomy. We got a major gift from Charles Simonyi, who worked with Bill Gates. He was one of the people that created Microsoft Office. So as you can imagine, he had a fair amount of money. He gave us a fair amount of money, and we named the mirror after him. And then, because everybody was familiar with this acronym LSST, we wanted to keep it. We just changed what the words meant. So it was originally Large Synoptic Survey Telescope. We renamed it the Legacy Survey of Space and Time, and that refers to the actual scientific program that we'll carry out with it. So this is a large public-private multi-agency project. That's difficult and complicated in and of itself. The lead science agency is the National Science Foundation. Our original baseline cost for it was $473 million. Because of COVID, they gave us another $85 million. The camera was developed with funding from the Department of Energy. That was originally $165.3 million and another $50 million because of COVID. And then we got private funding of order $34 million, which was from Simonyi and also from Bill Gates and a few other smaller donors. And that was crucial. And it's actually set a paradigm that most other big scientific projects are finding now, because the way the government works, you cannot spend any money on a final article until the project is formally approved. But typically, you can't get formal approval until you've demonstrated that you can build the difficult things. So it's kind of a circular loop. And you can't really get the money to do that. So we had to cut through that, and we did it by going and talking to rich people. That gave us an initial tranche of money that allowed us to build the mirror, which I'll show you what it looks like, which was really beyond what had ever been done before. And we did that. That was going to be the pacing item on the project, but we got that money early enough. It ended up being ready long before we needed it. So after building it, we had to put it in storage, which is another story in and of itself. Okay, let me start with what and why this project. So I used to give popular talks that were called Surveying the Universe. And it was referred to earlier that survey, was in the original history of astronomy. Like the basic question is, what stars are up there and where are they? That's now become the paradigm for modern astronomy. It's less about studying individual objects than it is about cataloging everything in the universe and cataloging it with high precision. So this is kind of a sea change in the way we do astronomy. In addition to making detailed observation of stars, we're now attempting to take large surveys of the entire sky. This really began in earnest with the Sloan Digital Sky Survey, which is a pioneering project developed in the early 2000s. And it will culminate in the project that we're that I'll describe for you today, the Vera Rubin Observatory. And for reasons I'll mention later, this is sort of the ultimate ground-based observatory for surveying. There would not be a point in building anything bigger. The reason is that if you build something bigger, you run out of galaxies. There are no more galaxies to see beyond what we can see. They get too confused. So we will detect 20 billion galaxies and about 17 billion stars. It would be the first time in human history that we know of more things in the universe than there are people on Earth. So everybody on Earth can own a few galaxies and own a few stars. There's plenty to give away. The data that we required are likely to transform nearly all fields of astronomy, from our understanding of the formation of the solar systems to the structure and evolution of the universe as a whole. So this is a really all-encompassing project. Now, I mentioned Vera Rubin. For those, many of you may be familiar with Vera. She was a pioneering female astronomer whose work provided some of the most convincing evidence for the existence of dark matter. Dark matter is a dominant form of matter in the universe, but it's fundamentally different from all the matter we're familiar with. We still don't know what dark matter is, but we know that it exists and that it dominates the mass of the universe. We only know of the existence of dark matter because of gravitational forces that it appears to exert. So one of the questions is, we know it's a particle. We don't know how that relates to any of the fundamental particles we already have. There are a lot of ideas that have been tested and failed. So it's still a big question, and it's one of the biggest mysteries in modern physics. Vera's work was well recognized during her lifetime, but she never received the Nobel Prize, which is interesting. There are some other really impactful female scientists that never received the Nobel Prize and should have, and Vera is one of those. We're especially proud because the Vera C. Rubin Observatory is the first major national facility of any kind named after a female scientist. And the fact that that's only happened a few years ago is pretty amazing. Okay, so what is the Rubin Observatory? The idea is very simple. You build a telescope that can take very large format digital images of the sky very quickly. You have to look at one hemisphere because you're located in one hemisphere. For reasons I won't go into, we chose the southern hemisphere. And the idea is to cover the entire southern hemisphere of sky with an imaging survey every few nights. And to do that repeatedly over 10 years. So what we will get is 1,000 images of everything in the southern sky. And you can take differences of those images between different times. And if you compare them, you'll see everything that moves in the sky. So all the small moving bodies in the solar system. We'll get millions of asteroids, comets, and things along those lines. You also measure everything that varies in brightness in the sky. So we'll see all the stellar variations, stellar explosions, active galactic nuclei, all the really exotic phenomena that we've discovered so far. We'll have a huge census of that. And then you can take these 1,000 exposures and add them together rather than subtract them. Then you go extremely deep. After 10 years, we'll go to about 27th magnitude, which is only slightly less faint than the Hubble Deep Field. But this is for the entire southern hemisphere, and I'll show you what the impact of that is. And as I mentioned, that'll lead to the 20 billion galaxies and 17 billion stars. So what's unique about this telescope? The unique feature of the Rubin Observatory is what we call high étendue. And étendue is defined as the product of the collecting area of the mirror times the field of view of the camera. So it has units of meters squared, degrees squared, okay? And that turns out to be proportional to how quickly you can survey the sky. If you have a big mirror but a small field, it doesn't take you very long to get each picture, but you're only taking a small part of the sky on each picture. Equivalently, if you have a big camera and a small mirror, You can cover a lot of the sky in every picture, but you have to integrate longer to get to the same depth. So it's the product of the two that determines how quickly you can do it. So the Rubin Observatory is located on a mountain called Cerro Pachón in Chile. There's another telescope on that mountain, the Gemini South Telescope, which is an 8-meter facility. It's one of the bigger telescopes in the world. And so if you look at the Rubin mirror, our primary mirror is an annulus. I'll show you why later. It's about the same diameter as the Gemini telescope, so nothing particularly striking there. But on the same scale, this is the field of view of the largest camera on Gemini. This is the field of view of the Rubin Observatory. So it's the product of these two that matters. So in that metric, we're 10 times bigger than anything that's ever been built, and actually 10 times bigger than anything anybody even talks about building. So it is really the ultimate observatory. And when you get to 27th magnitude, as I said, you run out of galaxies. They either are too blended or basically they don't exist because of the birth of the universe and the development of galaxies with cosmic time. So this gives you an idea of what that depth gives you. So this is actually a simulation. I won't show you real images from Rubin, but I will show you real images from another telescope. We built a very detailed simulator for this project, partly to cover the systematics. This is 1/200th of the full Rubin Observatory field. So imagine 200 times this picture with those number of objects. And we get that every 15 seconds. Okay. So the data content is extremely large. When we started this project in the early 2000s, we thought it would be the biggest data set in the world. That turned out not to be true. Okay. There's a lot of big data around, so we're up there, but we're not the biggest. But one of the statistics I like is that our data volume will be a few percent of all the cell phone pictures ever taken by everybody in the world. That's still a pretty impressive number. And most people don't try to do science with their cell phone pictures, right? So that's the difference. Having a data volume that large and being able to query that data volume and do science with it is one of the challenges. It's what? Yeah, it's all in optical wavelengths. Yeah. So we actually have it's a 6-color survey. We have 6 filters that go from the UV limit to the infrared. So we go from about 300 nanometers out to 1 micron, basically. Okay, just to get an idea of the power of deep imaging. This is actually a field taken with the Sloan survey. This is real data from the Sloan survey. This was done in the early 2000s. This is also a real image. It was done by a different telescope, a facility called the Hypersuprime camera, which is in Hawaii. But it's at the depth of LSST, of Rubin. This is the same field. So you see what you get by going very deep, and then multiply that by going over the entire sky. And that's where the high statistics comes from. Now, the idea, as I said, is very simple. Just survey the whole southern sky. Why hasn't that been done before? And the reason is it's hard. We needed to find a really good site, one with good seeing and a high percentage of cloud-free nights distributed evenly over the year. And this is kind of key. Most sites are good for most of the year, but there's a couple of months when they're terrible. But if you're interested in studying time variations, you can't really have a part of the year where you can't observe. So it's pretty rare actually to find a site that the cloud cover is pretty evenly distributed and also low and the seeing is good. And the site we used was a developed site, but it had those characteristics. We needed to invent a new kind of optical system that could deliver a large collecting area with a large field of view. So the field of view of our camera is 10 square degrees. That's 40 times the size of the full moon in the sky. So if you imagine looking at the full moon, drawing a circle which is 40 times bigger That's one picture, and we do that every 15 seconds, as I said earlier. So that's hard. That requires a lot of control over the optics and the camera to be able to do that. We needed to invent a new kind of telescope mount, which was capable of rapidly slewing to new points in the sky without wasting time settling after each motion. We do two 15-second exposures, and then we move. And we typically move several degrees. For most big telescopes, you move a few degrees and they start wobbling like this, and you have to wait 15 seconds for them to settle down. So we need an extremely compact, stiff structure, and that really hadn't been done before. And our goal was to slew and settle within 5 seconds. We needed to figure out how to build what would become the largest digital camera ever constructed. It's 3 billion pixels. It's equivalent to roughly 1,500 of the highest resolution, high definition TVs. So to display one of our image at full resolution would take 1,500 HD TVs. We needed to figure out how to process, archive, and store enormous amounts of data of order a few hundred petabytes. The petabyte is 10 to the 15 bytes, 10 to the 17 bytes. That's far larger data volume than everything that's ever been written in human history in all languages. That's a relatively small data volume. The images are what count for much more data. But we not only had to acquire, store, and process those data, we had to make a catalog that you could query. So the catalog of objects with all the different observations is trillions of lines long. There wasn't a database technology in existence that could actually work at that time. And not only that, we wanted to enable rather complex questions, like complex queries, like find me all the objects that are near some other object that has this property and all that. That's where the data exploration is going to come. That's not an easy code to sort of develop. So we had a big staff. We spent $150 million just on software. There is no other previous astronomy project that ever spent that amount of money on the data system. Typically what astronomical projects do is they put all the money in the hardware, and when they run out of money for something, they take it out of the data system. And then the telescope starts working and you don't really have any software to use it. And you have to wait a few years and you develop. We couldn't afford to do that. Okay, so what's the science of this project? The science is infinite, essentially. Every topic in astronomy will be impacted by Rubin. But in order to design a system and set quantitative requirements, we chose 4 main themes. The first one is cosmological, probing the nature of dark energy and dark matter. The second is solar system, so taking an inventory of all the moving objects in the solar system. Then exploring the transient optical skies, this is the time variation. And then the fourth one is mapping the Milky Way. And the new element we bring in mapping the Milky Way is with 1,000 observations, even with atmospheric limited seeing, you can get incredibly accurate parallaxes and astrometry. So we can get down to the sort of few microarcsecond level just by these precise statistical treatments of large amounts of data. We sort of take over where Gaia stops, and that enables us to get distances to much larger ranges in the galaxy. And of course, those distances are fundamental to stellar physics and to understanding the structure of the Milky Way as a whole. So let me talk first about the cosmology. How do we study dark matter and dark energy? And there are various ways we do this, but one of the main techniques is through gravitational lensing. So this is a simulation of what a gravitational lens does. Some of you may know this. Einstein's theory of general relativity predicts that mass concentrations, the gravitational field associated with mass concentrations, will bend light. And therefore, if you have a mass concentration sitting in front of other things, you'll see optical distortions in it. So it's the same, the analogy is if you have wallpaper in your house and you hold a wine glass up to the wallpaper, the wine glass is transparent. So to zero order, you could say, I can't see it. But you know you can see it because you see a distortion of the wallpaper. So the same thing happens due to gravitational lensing. You look at a field of background galaxies, and if you have a mass concentration in front of it, you'll see distortions in those background galaxies. Now, if the mass concentration is very large, then you'll see distortions like this, where you actually see galaxies being pulled into rings. We know of objects like this. They're called strong gravitational lenses. But even if the mass concentration is not that large, you can see correlated distortions of individual galaxies. For any one galaxy, you don't know what its shape was and you don't know where it was to begin with, but because the light from neighboring objects in the sky goes through similar mass concentrations, you see correlations. And so when you do those correlations, we can actually produce a mass map of all the dark matter out to reasonably high redshifts. And that turns out to be useful not only for dark matter studies, but also for charting the evolution of the expansion of the universe, which is critical to measuring dark energy. So the term dark energy refers to an even more mysterious phenomenon than dark matter, the fact that the expansion of the universe is accelerating. This was discovered in the late 1990s, and it resulted in a Nobel Prize to one of my colleagues at Berkeley, Saul Perlmutter, as well as Adam Rees and Schmidt, I forget his first name, in 2011. One would naively expect the universe, of course, to be decelerating due to the gravitational attraction of all the matter in the universe, right? It's like throwing a ball up in the air. It slows down. If you throw it fast enough, it'll escape, but it still slows down because gravity is an attractive force. So if you see that the expansion of the universe is accelerating, then something's wrong. Now, it turns out that's compatible with Einstein's theory of general relativity, but only if the universe is filled with an energy field that has negative pressure. That's an exotic idea, but it's actually reminiscent of things that come out of theoretical particle physics, so it's not entirely foreign. We call that energy field dark energy. We have no idea what it is. It's another of the current mysteries of modern physics, but we know that it exists very well. It's been extremely well measured. Now, the only way to try to figure out what dark energy is to make more precise measurements of the expansion of the universe, of the cosmic expansion history. And there are various methods of doing this. You can measure the brightness of standard candles as a function of redshift, and there are objects called type 1a supernovae that you can use for that. You can measure the angular size of standard rulers as a function of redshift, and there are things called baryon acoustic oscillations that you can use for that. Or you can measure the growth of structures as a function of redshift. And so that's basically, as the universe expands, because gravity is an attractive force, the universe was essentially gravitationally unstable. Structures started to form and grow with cosmic time just by accreting surrounding material. That's a well understood process. You can predict it from Newtonian physics. It's a kind of clock that measures time as the universe is expanding. And then you can compare that to redshift, and you get a redshift time correlation, which basically gives you a very accurate measurement of the expansion history. The interesting thing about the Rubin Observatory is we'll do all of this and much more. Just this very large data set allows us to do many, many different kinds of tests that are all really independent. They have different systematics, and they converge on the same answer, which is a very precise understanding of how the universe is expanding. Okay, let me talk about the solar system. This is a very interesting plot. This came from the Sloan Digital Sky Survey. So these are asteroids, and they're plotted as a function of their distance from the sun in astronomical units and the inclination of their orbit, which is a measure of, sort of where they are in the plane of the solar system. What's interesting about this is the colors. They're false colors, of course, but they represent objects that have similar spectra. The asteroids have a lot of different characteristic spectra, but you can put them in classes, in these color classes. Now, if you measure the orbits of all the asteroids, you can project them forward, so you know where they're going to be, but you can also project them backward in time. And if you project them backward in time, you find all the green points converge. Similarly, the blue points and the purple points, they all converge. So all these objects are produced by impacts, by collisions that break larger objects into smaller pieces, and then those smaller pieces continue on in their orbits around the solar system. So this is a way of charting the history of the solar system. How did the solar system form from these larger pieces that eventually give rise to all these small bodies? This started with Sloan. We'll do this in much more detail with Rubin. The other thing that is interesting about asteroids is, some of them could hit the Earth. And that was a popular topic about 5 years ago. It's died down a little bit now. This is a plot of the distribution of asteroids as a function of size. And on the top, we also list it in terms of impact energy. So for an object of this size to fall to the Earth, that's equivalent to a certain set of megatons of TNT. Okay, that's how big an explosion it would cause. And as you can see, this is a log-log scale, so it's a power law. At the high end here, you're talking about 10 to the 8th megatons. That destroys the Earth. Okay. Fortunately, there aren't very many of those guys. The red line is our knowledge. So basically, all the really big stuff, we sort of know where it is. And we know nothing is coming very soon. But you notice when you get out to this sort of range, our knowledge becomes very incomplete. And these objects in this range are still really dangerous. If they are big enough to make it through the atmosphere, the smaller ones will all burn up in the atmosphere. Those intermediate ones are big enough to make it through the atmosphere. Of course, the most likely thing they'll do is fall in the ocean. They're not going to fall into a city. That's pretty unlikely. But they fall into the ocean. But an object of that size falling into the ocean will create tsunamis all over the world. So understanding this danger is still highly relevant. And the Rubin Observatory will give us a catalog of all of these asteroids with enough warning that we can sort of see what's out there and what's coming. And that hasn't really existed to date. And this is just a plot which shows what our goal is as a function of magnitude, et cetera, and basically makes that limit. Okay, the third topic is the transient universe, exploring, the time-varying sky. So this is a plot of a characteristic time variation versus the characteristic brightness variation. And there's lots of known kinds of variable stars in the sky. All these things have names. I won't go into a lot of that. But this is sort of more interesting. These are explosive events. And so different kinds of explosive events. Again, characteristic duration of the event versus how bright it is. And you see these are core collapse supernovae, these are type 1a supernovae, these are luminous blue variables, et cetera. A bunch of different kinds of objects that are known. The interesting thing about this plot is that we had room to put the captions here because there's nothing here. There's not nothing there because there's really nothing there. There's nothing there that we never had the sensitivity to look. So these are objects which are fainter and very short. That's a totally unexplored space. And every time we build a new facility that has capabilities we haven't had before in astronomy, we discover all kinds of stuff. So we're expecting that we will fill in this plot, and that will introduce a lot of new ideas. And then the last topic had to do with the structure of the Milky Way. So this is, how far out we'll get. We'll get out to about 200 kiloparsecs, where we can actually use parallax to know distances. That's transformative for the galaxy. And one of the ways it's transformative is that we'll see a lot of tidal streams. So if you look at this picture, this is from Sloan again. You see these streaks across the sky. Now what those are satellite galaxies to the Milky Way that over time fell into the Milky Way. And as they fall in, there are tidal forces that strip the stars out and leave a trail. okay? And so if you can do this deeply, the problem with it is that as you look toward faint levels out in the galaxy, there's a bunch of foreground stars. It's hard to tell what's in the trail and what's, so you need to be able to separate the distances. That will come from proper motion and parallax. And we'll be able to do that to much larger volumes than done before. So right now we know of, you know, a limited number of tidal streams of the galaxy. There are probably thousands of these. And we will find these in the data. And if you know that tidal stream, that's actually a trajectory of something falling into the Milky Way. So it's sensitive to the gravitational potential of the galaxy and therefore the dark matter distribution. So it's a really pretty fundamental measurement. Okay, so this is just a summary again of what this project will do. We'll cover the entire southern sky every 3 nights. We have a field of view of the camera of 9.6 square degrees. The survey will cover 18,000 square degrees. And we'll do this quickly, down to about 24.5 magnitude per exposure, and we'll do it in 6 colors, U, G, R, I, Z, Y, which go from the ultraviolet end to the infrared. As I mentioned, it's a very big data set. We'll generate about 20 terabytes of data per night. Again, the number of galaxies, 6 million orbits of solar system objects. We'll issue alerts every time we see a varying thing. The problem with that is that we'll issue about 10 million per night. So this is not something you're going to get on your cell phone. This requires a trigger, effectively. So there's software being developed to say, how do you take all those alerts, figure out which ones are interesting, but we'll issue them within the night so that other telescopes can follow up for those interesting things. And I mentioned the key areas. So, okay, this is a repeat largely of what it is, down to 27.5 magnitude. 90% of the time will be spent on this uniform survey, and then we'll spend 10% of the time doing more specialized things. This gives you this is a simulation of what kind of sky coverage we'll get over the southern sky during that period. The dark band here is the Milky Way, which we will do part of, but frankly, the Milky Way is just too dense in stars at this magnitude. They all blend together, and it's not especially useful, so we'll exclude a lot of the core of the Milky Way. And this is advantage of more sensitivity, actually. This is the same thing I showed earlier. So let me talk a little bit about the project. We started this construction project I mentioned in 2003. It had 3 main elements: an 8.4 meter telescope, a 3 billion pixel camera, and a very large data system. And also, partly because of the interest in NSF and partly because of our own interests, we also built into the project from the start an education and public outreach program that would develop tools so that these data were accessible to the general public, not only to the professional astronomers. The data system is really complex. Okay, so there are these prompt data products, these alerts that we have to process very quickly. Just to give you an idea, within 60 seconds of closing the shutter on the mountain in Chile, we issue alerts to the world. So that means we had to get the data down the mountain, all the way to our processing facility in the United States, process the images, find everything that's varied, issue the alert, all that within 60 seconds. That was very demanding on the latency of going through the various optical fiber networks, how we did that. It took a lot of engineering to get that to work. And then, of course, on a longer time scale, we issue the full catalogs and the data release products, which can be used for ultimate analysis of the data. And I mentioned that education public outreach was a key part of this project. So that includes formal education components, tools for schools to use, a big citizen science program to engage the amateur community to directly work with these data. Things like planetarium exhibits and general public exhibits and the planetarium. So a lot of different ways that the public can make use of this facility. All right, let me talk a little bit about it technically. So this is the mirror, and you can see this is the primary tertiary mirror. And you can see it's an annulus, and there's another figure in the middle. So the primary is this outer piece, and the tertiary is the inner piece. So the light comes in, reflects off the primary, up to a secondary, down into the tertiary, and then up into the camera. Okay, that's the process. Those three bounces are critical in order to achieve this flat fielding over 10 square degrees. Otherwise, you get very significant aberrations. This was the first time anybody had tried to make two different figures in the same monolithic structure with this sort of polishing techniques. The tolerances on this are really high. We had to guarantee that these two figures were concentric to within a millimeter. Now, if you know anything about polishing optics, this is really hard. Okay, usually you can make the surface you want, but it's very hard to control exactly where that surface is. Here you're constrained to do it because you have two different figures. For most things, you make one figure and then you can adjust it and align it. And we didn't have that freedom here. The mirror is actually a complex assembly. It's not just the mirror. The mirror is a honeycomb structure. And inside the mirror are these cells where we have elaborate actuators that allow us to change the figure, and also an elaborate thermal system that recycles air from the dome into these cells in the mirror. So the key thing here is that you want the mirror temperature to be the same as the surrounding air. If the mirror temperature is different than the air, it'll drive convection, and that convection will disturb the images. So you really want to keep things to within a degree of ambient. And that's hard because, of course, as you know, at night the temperature drops precipitously and then it comes up again as daylight approaches. So controlling that thermal evolution was a major engineering piece of this. And so this is the basic optics of the system, the primary, tertiary, the secondary. And of course, that's what you care about, but we had to surround that with some piece of machinery that could move it around. And this is what the telescope mount looks like. It's extremely short and squat. It's an f1.2 system.
What's the diameter?
8.4 meters. f1.2. Why so fast? The reason it's fast is because we already have one humongous camera. And if we had a longer focal length, we would have a humongous camera. And that was dominating a lot of the costs. So this was done to try to keep the field as compact as we could, given the very large field and the very large primary mirror. The telescope mount was built by a company in Spain. We did a lot of testing on site in Spain. They basically assembled the whole thing and went through a bunch of tests, then disassembled it and shipped it all to Chile, and we reassembled it in Chile. This was happening when COVID hit. So the camera had been built, tested in Spain, disassembled, and then we got stuck for 3 years, basically, because of COVID. That's what delayed it. We also had to sort of take a lot of care in how to design the observatory structure. So you can see it's a louvered dome. That's not terribly unique. But notice the odd shape of the building, which looks a little bit like an ocean liner. The reason for this is that the prevailing winds on the site come in this direction. So in order to have a really clean air over where the telescope is, you want all the energy dissipation in the building to be downwind. So that's what it led to. We actually are dissipating energy here. None of that is affecting the quality of the air in the dome where the telescope is. And it's actually a complex building. So this is you can see the telescope now in the dome. This is not out. There's a lot of other stuff in this building. As you may know, mirrors oxidize on timescales of about a year or so, so you need to strip the coating and recoat them. This is much too big to bring it down to any other facility, so we built a coating facility in the facility. So this is a full-size coding facility that we can bring the mirror down, bring it into the coding facility, recode it, and bring it up. And let me talk a little bit about the camera. I mentioned this is the biggest digital camera for astronomy ever built. The entrance lens to the camera is 5 feet and 5 inches. For a while, our project manager for the camera was a female. She was exactly 5 feet 5 inches tall. And so she liked using that figure next to the camera. There's a lot of stuff in the camera. There are 6 filters that are on a complicated wheel system that allows us to automatically rotate them in and out. There's an enormous amount of electronics in this camera. In many ways, it's more like a particle physics detector. We have something like 3,000 channels of electronics, which means something like 20,000 leads that have to come into the focal plane. Normally, people put the electronics outside of the vacuum that houses the detectors. Detectors have to be kept cold, so you keep them in a vacuum. We couldn't do that because 20,000 leads into the vacuum would have been almost impossible to manage. So we ended up building the electronics integral in the vacuum. That had never been done before for an astronomical camera. We had to figure that out. And then we keep the focal plane at minus 100 degrees C. The electronics are dissipating a lot of heat. We generate about 600 watts in this camera. We have to pull all that heat out. We have 2 different kinds of advanced refrigeration systems to do that. That was also new territory, to pull that amount of heat out in a constrained environment like that. This is a schematic that just shows a lot of the pieces of the camera. This is the fully assembled camera at SLAC, which we achieved about a little more than a year ago. There's no person in this. The size of this camera is roughly the size of this green area of the room. So it's kind of like a SUV type of size. And as I mentioned, that front lens is like 5.5 feet, so it gives you some scale. The focal plane consists of 189 separate CCDs. They're arranged in what we call rafts, units of 3 by 3. Each of these rafts is its own independent camera with the electronics that reads it out in the footprint of the detectors. So basically, all of those signals end up going into a single optical fiber that comes out from each raft. And we built it so that we could move the rafts around, replace any raft with any other raft if we need to do that to refurbish the camera. And this is the camera mounted on the telescope, which actually happened in February. So we shipped the camera last summer. It arrived successfully in Chile. We had a dedicated plane for the shipment. And we had one of our scientists riding with it on the plane to ensure they didn't do anything stupid. And then it had to be trucked up the mountain, which took a day. And then finally mounted on the telescope after being checked out in the laboratory on the mountain. Just repeat a little bit of what's in the camera: 189 sensors. We do 2 × 15-second exposures. This is a real picture, actually, we took with the camera in the laboratory at SLAC. So this was just with a pinhole. We did a pinhole and we used a photograph of Vera Rubin. And this is actually a digital picture on the full camera of that photograph. Actually, the resolution of the photograph is not as high as the resolution of the digital camera. So if you blow in, you don't see anything crisply. Just a comment about the data system. One of the key ideas here is that everything would be open source and open science. So this is a project that will feed data to the world, and we want people to be able to do what they want. We don't want to freeze the data system and make it secure and stuff like that. So everything was open source. And we wanted to support what we call the democratization of science. which includes finding ways to support researchers who are resource poor, not necessarily at the most endowed universities, time poor, community college teachers who have a high teaching load, few or no grad students, work in liberal arts colleges and other kinds of disadvantaged colleges. So we want this to be an instrument available to everybody and enable real astronomy to be done by a large community, not by a select few. And it's a very big community we have now. These are all the countries in the world where we have active teams of people engaged in the project. We created 11 science collaborations, which are independent organizations, but they're collections of scientists interested in particular areas that can work together. And then, of course, we have many people that worked on the project itself. Wait a minute. What just happened? I don't know how to get back. Oh, okay. Oh, right. Sorry about this. Yeah. I was near the last slide anyway, so. Yeah, right. We could build a telescope, but we can't work that far. Okay, so I just wanted to comment on the cost of this and where it came from. A lot of people obviously involved in it. I mentioned NSF and DOE. In the end, it was about 550 million from NSF and about nearly 200 million from the DOE, and then the 34 million of private money. The main organizations were AURA, which is the Association of Universities for Research in Astronomy for the NSF side, and SLAC, National Accelerator Lab for the DOE side. And we're just about to go into operation. So we will finish commissioning the facility probably this summer, early in the fall, and then we'll start the 10-year survey. It's going to cost us a lot to operate it. So each year it'll cost us about $36 million or so to operate it. So over 10 years, it's about 365 million each. Okay, and this is just the schedule. So everything we accomplished in 24, early 25, system first light. As I said, that happened exactly a week ago. And associated media splash, so we're going to have a press conference in Washington in June. We'll release the first images. And late 2025 is when we'll begin 10 years. Okay, let me stop there and thank you for your attention.
All right, wonderful presentation. I have a quick question. Why a CCD sensor versus like the CMOS that we're more familiar with?
Yeah, so part of the problem when you do a project which is going to take you more than 10 years, you've got to freeze technology decisions relatively early. At the time we made the detector choice, we were looking at CMOS. At the time, you can't use the standard CMOS. It doesn't have the precision. So we needed to use hybrid CMOS, which is basically a CMOS readout bump bonded to a silicon photosensitive piece. Those detectors were running about 300,000 a shot at the time. So from a cost standpoint, they were cost prohibitive. Also, they have a number of features that, and they still do, which are not great. There's an image effect. If you take a picture of Jupiter and then you take another picture somewhere else, you see a negative image of Jupiter. So there's a persistence effect. There's also there's a correlated noise effect between pixels because each pixel is its own readout. So CMOS is great for, conventional photography and things like that, but it's not yet ready for this, or it wasn't ready when we had to make the decision. But I should say that the CCDs we used were not commercially available CCDs. our requirements, there was nothing on the market at the time. So we had to develop the CCDs with vendors that could meet our requirements. That took a while and was expensive because every run of a CCD test is roughly $1 million. And we had to go through about 5 or 6 runs with 2 different vendors until we had routinely produced devices that met our specs.
Thanks, Steve. Great talk.
Yeah, thanks, Jim.
You said that you take 2 images, 2 15-second exposures.
Yeah,
what's the
so
reason behind
this is a very interesting topic, and it's actually controversial right now. So the original idea is we take 2 15-second exposures and then move to a new field. And the original motivation for that was because of cosmic rays. We wanted to clean the images of cosmic rays. Obviously, they'd be in one of the 2. So if you difference the images, you can take out all the cosmic rays. We learned since that you can pretty much distinguish cosmic rays topologically, so you can remove them in the software. You don't necessarily have to do that. But it drove the timing of the readout. One of the most difficult things on the camera is that we read out the entire 3 billion pixels in 2 seconds. That requires this highly parallelized system, which drove so many channels of electronics. Now, there's a, while we're reading out for those 2 seconds, the shutter's closed. So there's a element of the community that says, well, that's 2 seconds every 30 seconds. We don't want to lose that time. Why don't we just do a 30-second exposure and then move to the next one? And over 10 years, we'd get back a month of observing. We should obviously do that. I'm personally interested in fast transient events. In fact, I wrote a paper saying that if we see fast events, we could actually distinguish them based on their shape because of the way the atmospheric turbulence works. But if you don't do the 2 15-second exposures, you never know about those things. So there's a whole area of science that is enabled there. When I was director, I said, nope, the baseline is 2 exposures because I wanted to ensure that we built it to have the capability. It's twice as much data than the other thing. And, but now I'm no longer director, so my voice doesn't count quite as much. There's still a community that wants to go to the 30 seconds. I've convinced them, let's run for a while with the 2 exposures and see if we see anything. And if not, then we probably will go to a single exposure.
Thank you.
So I have a question about dark matter. So how is this going to detect dark matter? By the motions of?
So we'll see dark matter in 2 different ways. Okay. Well, actually, the principal way we'll see dark matter is through gravitational lensing. So it's what I was explaining with the wine glass against wallpaper. So even though it's invisible, you see the distortion, the gravitational distortion of the background field. And that actually gives you a pretty precise measurement. We now know how to do it well. And so we can make dark matter maps as a function of redshift. And then we can study the statistics of the dark matter, which gives us information about dark energy, actually, because it constrains the evolution of the universe.
Who was your optical designer?
Actually, we had 2. The guy who I think did the most important work on it was a guy named Lynn Seppala, who worked at Lawrence Livermore National Lab. So the large lenses in the camera actually were managed by Livermore. They were fabricated in industry, but managed by Livermore. And the reason is Livermore had developed an outstanding optics capability associated with the NIF laser, because they had these entrance windows that were quite large that they brought the laser through to, for the fusion. And I mean, their requirements were that their lenses had to withstand enormous amounts of energy. So they had to be very pure very pure glass, so that there were no impurities that would get heated by the laser. We, of course, didn't have to worry about that. But in that process, they had learned how to fabricate and test large, thin optics, which is what we did it. But Lynn Seppala was an optical designer at Livermore. He's retired now. and he did the final optical design.
Okay, I have a question on Zoom from Sean. He says, after the 10-year survey, are there any other applications that might be appropriate for this type of telescope and camera that could be considered, or is the focal length limited to a sky survey?
Yeah, no, it's a very good question, and it's something we've been thinking a lot about. So, you know, nobody ever throws away a telescope. They keep running forever because there's always enough things in the sky to look at. This telescope is a little strange, though. So we've looked at, you know, because it has this well-defined survey, and as I mentioned, it's statistical. And so for a lot of the science, if you think about what would you get by running a second 10 years? You get the square root of 2, which is not enough of a big deal to pay the operations cost. So just running it longer doesn't necessarily make a lot of sense. Then we thought about, well, you could replace the camera with something else. The obvious thing to replace it with is a spectrograph, a wide field multi-object spectrograph. For technical reasons, this very, very fast optical system is not very well suited to that. I mean, it can be done. It's not impossible, but it's not necessarily the right way to do it. So you're probably better off building a telescope for that rather than adapting this. We thought about replacing it with an infrared camera. That has some attractiveness, but you can do infrared much better from space. So, you know, we sort of came away with like, there's not really a obvious thing. What I think has the most chance is we can replace the filter set with some narrowband filters and look at nebular emission in a galaxy. It'll be fantastic for that. So we can map all the nebular emission in a galaxy. That might be what we do, and that's not especially expensive. So that's a possibility. But the other problem is if you stop using the telescope, you try to mothball it, it's a health hazard, right? It quickly gets infested with rats and all kinds of other things, and you spend a lot of time just taking care of a dead thing. So then you want to demolish it, return the site, and you know that's another 20, 30 million just to decommission it. So we'd like to find a use for it because it's too expensive to throw it away. And we're still trying to figure out that. Yeah.
So two questions. One would be, I assume after you describe the camera, that has to have like darks, flats, and biases. How often do you have to take those and refresh those?
We did a lot of those in the lab. We can take darks during the day, and we do that routinely. There's also a standard dome screen, which we can look at to flat field, but we also built a custom projection screen that uses tunable lasers to bring monochromatic light down into the system so we can calibrate the absolute photometry that way during the day. And we'll do that most days. And we can move those spots anywhere. So there's a lot of lab benchmarking that we did, not just calibrating off the sky, but anchoring that with lab measurements.
Okay. And then the second question is, would you ever move it to the northern hemisphere to do the same survey?
Yeah. So we got asked that. Actually, there was a Korean group that wanted to clone it, to have it in the north. But, you know, actually it's, again, just the square root of 2. We're going deep enough that, I mean, if you're looking at nearby stars or even a galaxy, then the northern hemisphere is different than the southern hemisphere.
Right. That's
when you're looking at galaxies of redshift 1 or so, the northern hemisphere is the same as the southern hemisphere. So cloning it or bringing it to the north or redoing it in the north, you get the square root of 2 for a lot of the science, which is not worth it. So I don't think we're going to do that. Yeah.
Even though there might be phenomena in the north that you didn't see in the south?
At the level that, so for the cosmology, there won't be.
Right.
For the transient stuff, there won't be either, because we're going faint enough that the populations we're looking at are almost certainly extragalactic. And so they're going to be isotropically distributed around the sky. So you'll see half as many by looking in the south, but you won't see anything qualitatively different. The solar system stuff is interesting because the ecliptic transcends the north and the south. So we don't have complete access to the ecliptic from the south. We get most of it, but there is a little piece in the north that you could do. Yeah, but it's probably not worth building a new telescope or moving it. Yeah.
Hi. The question I have is the scale of everything related to sort of computer part of that. It's just staggering amount of data, and then you have networks and fiber optics, so on. How is reliability built into the system, such as data backup and network problems and everything else?
So we have fully redundant networks to bring the data from Chile to the States. There's two different paths. One goes through Brazil and then through Florida. Another path comes up the Pacific. We can use either or both. The only non-redundant path is from the mountain down to the base facility, to the coast. We built that line ourselves. That was $10 million just there, put that fiber optic line in. And that's non-redundant. On the other hand, we have storage capability on the mountain of order a week. So if we lose that line to the base facility, we'll store the data on it. We can process it on the mountain as well. And then we'll repair that line, get it that way. So we might lose a little bit of the alert capability, but we won't lose much of anything else. And actually, the networking was an interesting thing because we contracted with some companies in South America that were various pieces of the network line. One of them was a Brazilian company, but midway through this project, we started to get calls from 3-letter agencies in Washington that were concerned about the data. Because, of course, by looking at the sky, we see everything that moves in the sky, which means we see all the artificial satellites in the sky. So there was some concern about, you know, should our data be protected because certain places could get access to this and learn something about space assets. It turns out that's largely a question of how long you delay in releasing the data. So if you wait something like a few days before you release it, pretty much the data you would use it doesn't help you anymore. The orbits have changed enough. But for a while it caused a hiccup because they didn't want us to use this Brazilian one because we couldn't control it. It was owned by another country. And so that was one of the many, many programmatic problems I had to solve over these years. Yeah.
Okay, we have maybe 2 or 3 more questions before we run out of time.
With the steering committee on the research, was there ever talk about cross-pollination of the results coming back from the James Webb Telescope and what will come back from the Rubin and what synergies might be anticipated?
Yeah, so now, I mean, there's a lot of investments in astronomy and they're expensive. And so, yes, everything is working with everything else. So in particular, aside from James Webb, which I'll come to, there are other spectroscopic surveys we'll combine data with. There's very interesting work in combining the data with the cosmic microwave background, which is separate facilities. James Webb has a much smaller field of view, so it can't do surveys of the sky like Rubin, but it can follow up with incredible precision in the infrared, extremely high spatial resolution, and great spectral capability. So this is where the alerts come in. So, and the problem I said is we issue 10 million of these a night. So you need a filtering system that sort of uses other information to say this one's interesting and the rest of the stuff's boring. The one that's interesting, then you want to get Webb on, you know, quickly. So that's something we're kind of working on now, how to arrange that. But that will certainly be a big thing. Webb has been fantastic. I mean, you know, it cost $12 billion, went way over budget, but it is fantastic. And so the data coming from Webb are really amazing. Webb does see some of the first galaxies formed in the universe. They go to higher redshifts than we do. mainly because of the infrared capability, because the light gets shifted into the infrared. So it's complementary. They're not redundant at all, but we certainly will work closely with both.
I had a question about the alerts you just mentioned. Are they done based on comparison with previous images, and you're looking for changes, basically?
Yeah, so what you do is you take all the images you currently have of that part of the sky, and you produce one image, master image, which is constantly evolving. And then each new image you get, you difference against that previous reference image. And that's tricky because the seeing has changed and other stuff. You have to adjust it to get that to work, but you can do that. When you do the difference imaging, everything constant goes away, and you only see the things that have changed. And so that's where the alerts come from.
All right, thank you very much, everybody. Thanks for coming. All right. Hope to see you guys up on the mountain. Otherwise, we'll see you at the next general meeting in May. Have a good night. Clear skies.
Great. Thank you. Yeah, great.
I was just imagining Hallie just sitting in the audience going,
Yeah. Well, of course, they could do things a lot faster then.
thank you. Fabulous.
Great, thank you.
Great talk. Is there a dedicated data center?
Yeah, it's flat. It's flat.
Flat?
Flat.
Flat. Oh, okay. And how much heat will all this?
Yeah, that's the data center is a big thing. We built a special building for it.
Okay.
Which is, reduces the cooling cost for it. But there's been a lot of progress in big data with AI and stuff like that. So originally, there were a lot of problems we thought we had to solve that basically other people would solve them anyway. So some of the, this happened over time, so we couldn't benefit by it because we had to make decisions when we had to make them. But there are elements of the data system. If we did it again now, we would probably change it again, given what now it's doing.
Great talk.
Great.
Really appreciate it.
Yeah.
Take care.
Yeah.
Congratulations. You never asked me. I just to let you know. I'm not
Very nice, Steve.
Oh, thanks, John. Thanks for having us. Yeah. Are you retired now?
Yeah, yeah.
Yeah.
I do a lot of outreach.
Yeah, so have you followed what's been happening?
Yeah, from 30,000 feet.
Yeah, I know.
As close as I want.
So
I mean, the latest thing,
no, I
that's
mean,
just coinciding, but so they've been looking at it in Chile.
Yeah.
And